And this is a talk by James Robbins. And the title is A Proof of Wells Inequality in Quantum Mechanics Using Causal Interaction. Please.
Skip some of this. Okay, first, full disclosure. I don't know much quantum mechanics. A colleague of mine proved something about causal interactions, and for some reason I realized it could be used to prove Bell's inequality. And the idea was not new, was to recast interference between treatments. Oh no, this is to cast interference between treatments as a question about causal interactions. That'll come clear later. And we wrote a paper, and Richard Gill, who's actually an expert in these stuff, is an author also. And the proof's simple. There are many proofs of Bell's theorem that are simple. So the only reason to add this is to highlight the connection with the current causal inference literature. And I don't necessarily mean the causal inference literature you've been hearing about, not the graphical causal inference literature. There's a whole different causal inference literature based on counterfactuals. So this will be, to those who don't know quantum mechanics, they'll be glad that I'm going to go very basic. To those who do, I can only say it's your chance to learn about how epidemiologists and statisticians think about causality and how it relates, and a way it relates to physics here. Okay, so I'm going to go very fast because you all know this, because I haven't been given this talk to physicists. So, okay, so short history. There's a non-intuitive implication of quantum theory. Pairs of spin 1/2 particles can be prepared. And if the particle separates, we measure the spins of both particles along a common axis in space. And the measurement of one particle's spin always perfectly predicts the spin of the other, because the total angular momentum has to be 0. So the first particle spin is up, then the spin of the other one must be down by conservation of angular momentum. And one explanation is the measurement itself of the first particle determined the spin of the second, even if physically separated by light years. And that would mean, if that was true, that reality in some sense was not local. What occurred at one place would affect reality, i.e. the spin of the second electron at another. So, and Einstein believed in local realism, and he argued both particles are carrying with them from their common source. Remember, they were one thing, they broke it to 2 electrons, different spins. That they're carrying with them from their common source hidden correlated spin outcomes, which they will exhibit when measured. And Bohr disagreed with Einstein and his local realist assumption, and neither Einstein nor Bohr at the time, as I understand it. Also, if there are any physicists here who want to interrupt when I get the story wrong, feel free, because this is close I could come, but neither Einstein nor Bohr realized the hypothesis of local realism was subject to empirical tests, and Bell showed that it was possible, and he proved their strict locality were true. There would be certain inequality constraints between measurable quantities that must hold. Quantum theory predicted these equalities must be violated, and experiments found Bell inequalities were indeed violated, and Einstein was wrong, and local realism is false. Okay, now, relationship to Neyman's counterfactual causality. We have 2 particles. We can measure the spin of each along any axis. So the treatments, X1 and X2, are going to be our interventions. So, and they're going to take 3 values, 0, 1, and 2, just representing different 3 angles. X1 records the angle, axis in space, particle 1 is measured at. X2 records the angle particle 2 is measured at. So we have a treatment for particle 1, we call it X1, particle 2, X2. Okay, and our responses is after we measure the particle, is it spin up? If it is, so if y1, when you treat particle 1 with x1, particle 2 with x2, y1 is going to be, that's a counterfactual from our point of view that could have interference because I'm making it depend not only on the treatment that particle got, x1, but it may depend on x2, is the binary spin. That's the outcome, which is 1 up if it's up and -1 if it's down. And it turns out quantum mechanics, you always get either 1 or -1, no matter what angle you measure it at. And y2, x1, x2 is the spin for particle 2, 1 or -1. So in the language of deterministic name and counterfactual model, YL, with L being 1 or 2, is the counterfactual response of particle L under the joint intervention x1, x2. Okay, so then what's the experiment? We prepare n entangled pairs of particles. That just means they came from the same place and they're just what I said, their total angular momentum is 0 for each pair separately. So investigator 1 flips a fair coin and measures particle 1 in direction 1 if heads and in direction 0 if tails and records y1. Investigator 2 flips a second independent coin and measures particle 2 in direction 2 if heads, in direction 0 if tails. So if tails, they measure them both in direction 0. If they measure them in 2 different directions, if they don't do 0, x1 always measure, the non-zero measurement for x1 is always angle 1, the non-zero measurement for x2 is always angle 2. Okay, so then we're going to see data. So we're going to see the data from the experiment. We're going to look at the joint distribution of the spins 1 and 2 given the angles x1 and x2. Okay, and by randomization, to get to in a minute, x1 and x2 is independent of the counterfactuals in the usual way. Although I think one of the talks mentioned it, one of the theories of why Bell's equality may not be whole is called conspiracy, which means the whole universe has been constructed to do weird things from the day of the Big Bang or before, but that would mean people don't have free will and can't randomize. They're forced to do what the universe wants them to do, but no one believes that as far as I know. So here we take, so we're going to assume we can randomize. So here we take, so usually I'm just going to give the results in terms of the distribution of the counterfactuals because you've just seen that connects directly to the distribution of the data under, given that you randomized x1 and x2. Everybody with that, right? So I can say the mean from the experiment, I can learn in hypothetical repetitions, doing more and more pairs, I can learn the mean of these counterfactuals because it's a randomized experiment. Okay, so now we're going to consider the hypothesis that the outcome of particle 1 doesn't depend on how particle 2 was measured. So that's, you don't have interference in our language, and the outcome of particle 2 doesn't measure how particle 1 was measured. So that's a null hypothesis of no interference. And remember, these measurements are across the universe, and just so you get the punchline, there is interference. Okay, so in the language of counterfactual theory, this is a hypothesis of no interference between treatments. In physics, it's referred to as a hypothesis of no local hidden variables. I'll come to that.
Do you like to refer to the hypothesis that the hidden variables are local? Because to say that the hidden variables would fail to be local is exactly this. So I think maybe you can say that it's the hypothesis of local hidden variables.
Of local, what did I say?
You said of no local hidden variables.
Oh, the hypothesis, of only local hidden variables. Sorry, you're right. Okay, we shall see this hypothesis experimentally testable through Bell's inequality and one test gets falsified. So why do we call no interference between treatments? That's what we call it. Why do they call it local realism? So, okay, so as I said, the particles can be separated by light years. You can't pass information, whatever that means, faster than the speed of light. We'll get to that later. So, so the hypothesis of no interference between treatments implies reality. The hypothesis, no, but reality is local. It's the other one that's, I don't know, I kept saying that backwards. Okay, so the hypothesis of no interference between treatments asserts both local, this is correct, locality and reality. Okay, it asserts locality because the angle x2 at which part of 2 is measured has no effect on the spin y1 x1 of particle 1 because we have no interference. And if we assume deterministic counterfactuals, it asserts reality because the spin yx of a particle measured along axis x is assumed to exist for every x, even though only one's observed. So that's having a deterministic counterfactual. We only observe the one corresponding on which particle is measured, as we say, we only observe the outcome under the treatment.
Sorry, this is something Bell insisted on. Sorry. This is something Bell insisted on many times. The deterministic counterfactual part, that's not an assumption, that's a theorem. You assume locality.
Yeah, I'm not
perfect.
Let me do the theorems. I'm not that confused.
What you said is that 2 assumptions are made, and it's not true. Only one assumption is made, a locality assumption. That's the only assumption.
Okay, let me go on and see if I do it wrong when I get to it. Okay, so Einstein's famous dictum, God does not throw dice, makes it clear that he believes in a deterministic and not a stochastic counterfactual. And I think deterministic counterfactuals correspond to what Einstein called the elements of reality, local, and they were whatever angle you measured at, their outcome was determined. In fact, Einstein deduced the existence of deterministic counterfactuals under locality. Why? Well, consider the hypothesis that YL for some 1 or 2 is a realization of a random variable that is 1 with some probability rather than being deterministic, some probability less, between 0 and 1, and -1 with some other probability. That is, say you believe in stochastic counterfactuals. Well, given that Einstein believed in the hypothesis then of stochastic locality, he's going to rule out stochastic proof. Then he has P1, the probability particle 1, goes, is up or down, given x1 and x2 doesn't depend on the other place. So we have no interference. So we're still going to do no interference between treatments for stochastic counterfactuals. Under this assumption, he deduced that God does not play dice from the fact that we always get a negative correlation between y1, the particle here, and y2. Remember, if they're measured along the same axis, I is the same axis, one's always up and the other's down, or vice versa. They have correlation -1. So they couldn't be having probabilities that were different between 0 and 1, because if they did, and there was only nothing non-local could happen, how could they always know what the other one is doing? Okay, so you can deduce determinism from locality. Maybe that's what you were saying. See, I'm not as bad as you thought. Okay, so proof of interaction between treatments by results of causal interaction. Okay, so first, data on correlation between the 2 outcomes is going to be critical because, as a fact of nature, that's the only place where things are non-local, where we have interference. So I'm going to use an outcome that looks at how often the 2 outcomes are equal. Okay, so it's the indicator. So I have two outcomes. I'm going to take the indicator whether they're equal. And so m x1, x2 is 1 if they agree, both up or both down. M is 1, otherwise 0 if they go in opposite directions. And I think this is and suppose our particles are in a maximally entangled state. They're certainly in entangled state. I don't know that it's maximal. Then according to the quantum mechanics of the two-particle system, the mean of the counterfactual, Mij, so it's the product of y1 and y2 when you force y1 to have angle measured at angle I and y2 measured at angle J is this is just from quantum mechanics, which we don't know, but this is a fact of quantum, that it's the sine squared of the angle between them. Delta Ij is the angle between the directions, okay? And this result has been confirmed by experiments in which the angles of measurement were randomized. And notice in sine 0 equals 0, if I measure them both in the same direction, I get that they're opposite, that their spins are exactly opposite, as we said already intuitively, but I'm just pointing out that formula agrees because if it's m is always 0, and that means they have opposite spins. Remember, opposite spins is m of 0. Okay, so we can take the mean of this outcome, this single outcome now, the indicator of whether they have the same y1, y2 with the same spin. We're going to take its means as data from the experiment. So we did a huge experiment, and we really were able to randomize. Okay, so we show this is incompatible with local realism, refuting the hypothesis of no interference. And the following unit may be taken to be a pair of entangled particles. So think of a unit now, because this can be part of the subtlety, as the pair. Okay. Okay. So theorem 1 is if I'm going to always take Mij as 0 or 1. Remember, it's either 1 if they agree, 0 otherwise. If I have m when I measure particle 1 at angle 1 and particle 2 at angle 2, if that's 1, but all the other m's, both zeros, a 0 with 2 and a 1 with a 0. Remember, we never measure particle 1 at 2, and we never measure particle 2 at 1. So these are all possible treatments. There are only 4 things. If this one's 1 and the rest are 0, then the hypothesis of no interference between treatments is false. So suppose the hypothesis holds, then M12 is 1, implies that both Y1 and Y2 are 1 because they agree or they disagree. So we're thinking of one pair, no random, no experiment. This is completely deterministic. Okay, and I'm saying I'm going to from one two-particle unit, I'm going to rule out. If I get this sequence of outcomes, then I know there's interference. Okay. And a lot of ways to see this. This is trivial, but let's do it. I'll do it this way. Okay. So let's take case A. They both agree because they're up. Okay. Both spins up. That gives, okay. So suppose A holds, then we know M02 is 0, and we know that Y22 is 1 because they're both, Y2 is up when you treat it. We'll call 1 and 2, 1's the treatment for 1, 2's the treatment for 2. Okay, so we have to have -1 because that's 1, and they disagree when I treat particle 1 with 0. So I get a disagreement. Well, Y2 was 1, so Y1 when I treat it with 0, that says 0, and 2 has to be -1, or we want to have M02 equals 1. Now, if we look at M10, we know that's 0 because we assume there's such a person. But we know y1, 1 is 1, and that implies, by the same argument, that y2, 0 must be -1. But if y2, 0 is -1, and m0, 0, we also said was 0, that implies that y1, 0 is 1, because remember, if you have 0 and you measure the two particles at the same angle, they're perfectly anti-correlated. So I measured at 0, I got -1 for y2. That's because I learned that here. And by this being 0. But I know whenever y2 is -1, when I measure 0, if I measure both at 0, y1 has to be +1. But we just deduced that y1, 0 was -1. That's a contradiction. So what went wrong, the only thing that could have gone wrong, is I should have had two indexes. That is, local reality was false. It was incorrect. You know, because if I had it, if I allowed each individual y to depend on both I and j, I wouldn't have had all these constraints that led to a contradiction. So the contradiction is, once again, if when you treat both, their spins agree, but any other combination of treatments, anything with a 0, their spins disagree, and that's impossible just by simple logic on a local if the outcome doesn't depend on both treatments, because you get a contradiction. I did, you know, I did this case, but the other case is isomorphic. So but I don't know the outcome of one particle, do I? So if I knew there was such a particle, I've rejected local realism. But how am I going to tell from data there's such a particle? So can we use the empirical data to deduce there must be a unit satisfying that, because that rejects no interference, therefore local realism. Okay, the answer is the following. Suppose, okay, remember Mij for every treatment Ij is always 0 or 1. So if I could show you that the difference between these means is greater than 0, then there must be a unit with those, with all three of anything that has 0, 0, and when you treat both being 1. Why? Well, I mean, it's pretty clear, but by contradiction, suppose there was no unit that had what we cared about, okay? Then for all units, so first you can see if this guy, so this difference will always be 0 if there's no such unit, because if we are subtracting non-negative numbers, so the only way this thing could not be 0 if this guy was 1. But if it's 1, that implies at least one of these guys is 1 if we have no interference, because these guys, this being 1 says I'll also get 1 for the one of these that agrees with let's say it wrong. Okay, this is trivial. So you have to have one of the other m's be also 1, because because I said they can't all be 0. That's it. My hypothesis, right, that I'm rejecting by contradiction, says I can't have this one and all these guys be 0, right? So at least one of them has to be 1. Now look at this. Look at the thing I'm trying to get. Then this thing is going to be less than 0, because if I ever have this one 1 one of these has to be, at least one of these has to be 1. So I can never be greater than 0, okay? So if there's local reality, no interference, this mean has to be less than 0. But quantum mechanics says, or to put it another way, okay, I already said you can get a trial. Quantum mechanics says, wherever I go, that that's not true. Just remember that the mean of Mij is sine squared. So if I look at these means, which has to be less than or equal to 0 under local, under no interference, I get instead this minus 0, because M00 always gives you a minus, because measure the same angle, they're anti-correlated. And then so all you have to do is see if there are any angles that satisfy this greater than, should be this plus the typo, that plus that. And it's easy to try some angles. It's not hard to find them, okay? So the empirical facts mean that local reality is wrong. Again, that's because this being positive, those implies there's no individual. There is an individual, sorry, who has 1, 0, 0, 0. And because there's such an individual, we saw that's incompatible with local reality or no interference. Okay, so the point is, I didn't really have to do any probability here, right? So there have been a lot of proofs like that. Okay, what's the connection? Okay, I already said it here. Okay, okay, theorem 2, that's the one that says you want to know, you want to prove that someone has 1, 0, 0, 0 and 4 outcomes, okay, that you can empirically test that from a randomized trial, so you can see the counterfactuals by, because we know, you can falsify it, you can prove it, because we know that if it wasn't there, this difference in means would have to be, whatever the theorem was, would have to be less than 0, but it's not in quantum mechanics. Okay, so we've disproved local realism. And the point is, theorem 2, the one that says if you want to know 1, 0, 0, 0, you can show that somebody exists, that is, there's no local realism for some pair if that contrast is greater than 0. And this, to me, was first written in the statistics literature about the interaction of 2 treatments. So you're thinking of, so the paper by Tyler, there's one outcome, and I have a genetic exposure, environmental exposure of 2 genes. I think I say 2 genes below, 2 genes. And he says if there exists a subject with a response M, so for him, M wasn't the product of anything, it's just the outcome of whatever he's interested in. You have a cleft lip for this kid who's getting 2 treatments, getting 2 genes. So it's not about, this theorem was not about interference between treatments. It was just about the effect of 2 treatments on one person. And so you have 2 treatments and he has some outcome M. And if M is 1 only when you get both treatments, but 0 otherwise, the definition of this case is said to be called an epistatic interaction in genetics. So this is something very interesting to geneticists. The outcome is cleft lip, 2 genes, M is cleft lip, 1 or 0. So the corollary to theorem 2, or theorem 2, the corollary is just you had a randomized trial, shows that if X1 and X2 are randomly assigned, it's possible to empirically test for such an interaction, although the test is not consistent. It's the converse of theorem is false. That is, if you get that expectation contrast greater than 0, you knew that there was somebody who had an epistatic interaction. There was someone like that. That's exactly the result I used to prove Bell's theorem, okay? And it wasn't until he wrote his paper that one could, it was known that you could empirically falsify the hypothesis of no epistatic interaction. So And so the above shows that the problem of testing for an epistatic interaction between two treatments within a single subject is formally equivalent to testing a hypothesis there's no interference between treatments. This is considered interference versus interaction, and one person considered quite different things in our field. That you can test the no interference between treatments given to two different subjects, I and J. These two subjects are the two electrons that we call a unit because we're looking at matched pairs. So this is an obvious, but previously, I think, largely unrecognized isomorphism between the literature on treatment interaction, the literature on interference between treatments. And at the time I wrote this, was probably no longer true. This was back in 2012. A lot more was known about interaction than interference. So there's a lot to learn here. Okay, so we've already done that. So there's something interesting to notice here, which I like, is notice that the sample space X1 I'm back to quantum mechanics. For X1 was 0 and 1, and for X2 was 0 and 2. That is, when 1 and 2 got treated, they would never treat it at the same angle. Okay, to a statistician, like, this seems an odd choice. For the sample spaces, as making both sample spaces 0, 1 is much more natural. Why do we call one of the treatments 2? And then you could write everything just substituting X2 equal 1 for X2 equal 2. It's just, okay. And if you look at the theorems I proved, they're both still true. So why did they do that? And it's the physics, not the math. The math of proving a contradiction, why is it the physics? Because if I had put X2 equals 1, that would mean M11 means now measure them at the same angle, right? The same treatment. And we know that's always going to be -1. No, it's 0. They can be anti-correlated. M is called 0 if they're not the same. So that's always going to be 0. So when I do my contrast, I'm going to get 0 minus 0. Those are the same. Those are the same. So I have to get a minus number. So I can't refute local reality, because I need, the way I refute it is that contrast is greater than 0 if I don't have a different angle for 1 and 2, even though the refuting theorem doesn't say anything about that. It's the physics that says M11 is 0. Okay. And now, just to show you how it's all goes together, I'm going to do a quick epi example of using the exact same logic of, interference, allowing you, showing there's interference. So here's an epi example. They're independent households of husband and wives, husband and a wife. That's the unit, okay? And there's no interference among households. They're like the experiment. They're like, every unit of 2 particles, okay? And I want to ask you the question. I'm going to ask a question. We're having infectious disease and there's a vaccination, COVID. Okay, are there households such that the husband and wife both remain uninfected if and only if both are vaccinated? Okay, that's a question. That turns out to be Bell's theorem. Because X1 is 1 if the husband is vaccinated, 0 not. X2 is 1 if the wife's vaccinated, 0 not. I no longer need them not to ever take the same value because we're not doing physics, okay? There's no anti-correlation with the husband vaccinated, the wife vaccinated, it's effective nature, okay. Okay, so in X1, X2 are randomly assigned. So I'm going to define Y1, given X1, X2 is 1 if the husband is not infected and 0 otherwise. So Y is 1 if you're not infected. And same for the wife, I call wife 2, that may be sexist, but anyway, I wasn't thinking about it at the time. Okay, and now I'm going to define M X1, X2 as simply the product of those two, not agreement, okay? I'm just going to use that outcome. So I'm going to ask, are there subjects with M11 equals 1, but all other combinations equal 0? Because if M11 equals 1, by definition, that means both of these were 1, and therefore the husband and wife neither of them were infected. That's the only way to get M11 equals 1, because I'm taking the product of something that's 1 if you're not infected. All these, one or the other, is infected. So if I could prove that there's somebody, so if I could prove someone like this existed in the population, that means that the husband and wife are both uninfected only if they both get treatment, 1-1, okay? Which is, okay, well, the answer is yes, if the same contrast is greater than 0, because I just showed you in a theorem that I can prove someone's like that if that contrast is greater than 0, because M has the same sample space and everything else. That had nothing to do with anything with numbers, okay? Okay, so I just did an interesting epidemiological example with exactly the same logic. So from our point of view, ruling out no interference between treatments also rules out local reality. And well, suppose the hypothesis of local reality therefore is false. Have we shown that we have interference? Well, we have interference by our definition. These counterfactuals have to exist. The outcome Y, when you measure Y for a given person, when you measure that person one direction and somebody else in another direction, they have to exist. And so if we believe these exist, then our assumption of reality remains. That is, these counterfactuals exist. If I tell you, the game I was playing is I always played that there was reality. That is, reality may depend on measurements across the universe, but there's reality. And as given the reality of the Neyman model, there are those counterfactuals. The cause had its, in some sense, effect faster than light speed, although, okay. And now, it's important, okay. So the bottom line is there are a lot of interpretations of quantum mechanics and these people that don't believe in these counterfactuals, even the non-local counterfactuals, okay? So they agree local reality is not true, because that argument still goes through, because the argument was, I made the argument about a hypothesis of local, that the outcome of the spin particle 1 only depended on 1, the outcome of the spin particle 2 only 2, and it was deterministic. There was an element of reality because of the anti-correlation. There couldn't be probabilities, but the question is the model with counterfactuals, depending on both measurements, true, or I guess as there are a lot of theories. I think the Copenhagen theory says, no, nothing exists till you measure it, sort of. There aren't these counterfactuals, but okay. And another interesting thing, which is the no signaling assumption. So we know that Y1, X1, the way it's going to come out in some sense depends on which angle you measure the guy across the universe. But interestingly, so that means there's an effect of 2, but it has no effect on the mean. The mean of Y1, X1, when I measure 2 in direction 0, is the same of person 1, whether I measure 2 in another direction. That is, the way we did this is something like the Neyman null rather than sharp null. You don't get an effect. Okay, and that's called no signaling, and that's important because if you could do that, you could transfer information faster than light. You could probably kill your own grandfather, because here I am many years later, and what I measure here can affect something way over there, and if things faster than light, I don't know, go back in time. And so you could kill your own grandfather. So it's sort of probably pretty good that no signaling's there. Okay, do I have anything else to say? That's enough. I'm not going to worry about the rest of it. Okay, I'm done.
So let me just, because you ended with the grandfather, and that awfully sounds strange, right? For someone to say, gosh, if blah, then you could kill your grandfather, right? That would be pretty bad. That doesn't follow. I just want to say, look, that doesn't follow, right? If we
Okay.
conclude that nature, which I think is the correct conclusion, nature is not locally causal or Bell local, then
Wait.
you have to put some non-locality to the physics. One easy, simple way to do it is to put a preferred foliation into the space-time. That's kind of non-relativistic, but that's the natural thing to do. And if you do that, you can still have that causes always precede their effects. Relative to that foliation, there are no causal loops. There's all your directed graphs are still acyclic. You don't get any paradoxes like that. It's very straightforward, right?
Wait, you said there was you snuck in something. You had to have foliation, and what else? You had something else.
No, just you have a foliation, and the causation is that causes always precede their effects in that foliation.
Okay,
And therefore you can't get loops, okay?
foliation is a foliation.
Foliation is just a slicing of the space-time.
So if I think there's a Big Bang,
yeah,
that would make a foliation.
no. You take the whole space-time, right? Picture it in your head.
Okay.
Slice it into a set of more or less horizontal slices, okay?
Yeah.
Foliation just means divided into leaves,
Okay.
okay? It corresponds to what Newton thought the way time worked, that there's an instant of time, and that instant of time is globally defined. And it cuts across your space-time diagram. If you put that in and do your physics in terms of that, you can make sure you can't kill your grandfather. You can make sure that all of your causal graphs are still acyclic, and you can violate Bell's inequality at space-like separation.
But can you violate no signaling also, right?
You can do it with or without signaling.
Well, let's do it with violating.
Yeah, you could violate signaling. It would be okay. You still couldn't kill your grandfather. You could signal from here to somewhere to the side outside the light cone, but you couldn't have a chain of signals that come back into a closed curve, because the source of the signal and the receiver would always have to be later in the foliation.
So I see. So if someone insulted me, I could tell someone across the universe who happens to be with that person's wife to kill his wife. But
yeah, but they couldn't then signal back to your grandmother and tell them to kill your grandfather. Okay.
Other questions?
Hi, Jimmy. I'm wondering why the deterministic counterfactual matter here. I understand in theorem 1 it matters because its statement is in terms of individual binary, but in theorem 2,
yeah. So
average.
Okay. So matters. Actually, that's part of the thing I didn't get to. I have. Okay. Suppose, yeah, so if you have non-local probabilities, is that what you're asking about stochastic? So they depend on INJ, it depends on the measurements, but you have a probability one's going to go off and so forth. Yeah, so that inequality that you see still implies that these guys can't just depend on one index. I mean, one way to do that is just that, because there's one thing with probability 1, because remember when you measure on the same angle, but in general, well, I guess that doesn't even play. In general, you can just do a coupling argument. Tyler and I wrote a paper on stochastic counterfactuals. If you looked at it, it's not going to change anything, because you can couple to a world where it's deterministic.
Yeah, because when you mention local reality at the beginning, from the English statement, there's nothing to do with deterministic counterfactual.
Oh, no, Einstein proved there was. If you had locality.
No, but can you go back to the slide? When you use English to describe local reality, you were just saying,
since I was saying it wrong.
You were just saying,
let me go to where
exists.
Yeah, so let me go.
No, at the beginning.
Yeah,
before
I'm trying to find
mathematics.
out where the beginning actually. Okay. It's the point where I said Einstein proved that it was deterministic.
Yeah, I don't know what Einstein proved, but what you said is like the English part does not match
Well,
the mathematics.
but let's go through the logic again. The logic is, we know as a fact that if you measure two particles along the same angle, one's always +1, one's always -1. Now, imagine we had locality. Locality just means that I measured particle 1 doesn't influence particle 2 and vice versa. Then I claim I've just proved determinism of the counterfactuals, because if these two probabilities have nothing to do with each other and they're not deterministic, why do you always get perfect anticorrelation? That's the argument that Einstein gave. So he decided the world was deterministic, and therefore within one of these electrons, the outcome it will have, no matter what angle you measure it at, was completely determined. And that's the right argument if there is locality.
Degenerate two-dimensional distribution does not mean it's deterministic. Just means the joint distribution is degenerate. Right.
Yeah,
You have two variables. You're saying.
No, because they don't have, their joint distribution is independent. If the measurement here is nothing, I mean, when they're anti-correlated, no, they're independent. They're exactly, no matter what angle I measure them, they're exactly anti-correlated, right? If I measure them at both. So they can't be probability, they can't be stochastic probabilities. I don't know. I mean, for the joint distribution, other than my y doesn't depend on what you measure over there and vice versa, okay? So that proves they can't both be probabilities. The probability is only depending on my measurement and this person's measurement that aren't 0 and 1. Now, you want to say something more. So I was saying no more than that. What you may, I'm not saying, I'm saying that's what I was trying to argue.
Okay, so
and I'm not sure what you're saying above that.
I think maybe this is a perfect opportunity to discuss afterwards, because we are already a bit over time. So I think it's time to thank James and all the speakers of the session.